Hi, and welcome to 8.8a Conservation of Energy 1. In this video, we discuss problems that have to do with the conservation of energy. Basically, what we've been doing is introducing kinetic energy and then different types of potential energy. We had gravitational potential energy and elastic potential energy. All three of those types of energies that we've been working on are going to combine into one type of problem, conservation of energy. So let's get to it. It says a skateboard with a mass of 3 kilograms and a velocity of 9 meters per second is traveling across the ground. Then it travels up a half pipe and goes vertically up into the air, reaches a maximum height where the velocity has a velocity of 0 meters per second, and then comes straight back down. It says to draw a diagram of the ramp. So basically you have the ground and you have your skateboard, very nicely drawn skateboard here. And then it's going to come up to a ramp, and then it's going to go in the air. So the skateboard is now, maybe it's all the way up here in the air. Okay? Its initial velocity is 3 meters per second. And then at the top, it says the velocity is 0 meters per second. So let's just pause here. The velocity is 9 meters per second. And the mass of the skateboard is 3 kilograms. So let's just pause here for a second. It has a velocity here, but no velocity here. This is where the conservation of energy comes into play, because we're going to be dealing with situations where there's an initial condition and then a final condition. So right now, this skateboard has kinetic energy. But at the top, their velocity is 0, so there is no kinetic energy. What happened to that kinetic energy in the beginning? Did it just disappear? Well, as you can see, it's in the air. It's a certain height above the ground now. So that means that there is what type of energy? There's gravitational potential energy. So all of this kinetic energy now becomes gravitational potential energy. Basically, if we know how many joules it has in the beginning, we know how many joules it has at the end. And that's the basic principle behind these conservation of energy problems. So in the beginning, how much gravitational potential energy is there? Well, it's not really a certain height off the ground. The wheels are touching the ground. So I would say that has no gravitational potential energy. So you can see it goes from kinetic to potential. So that's the idea. Now, for B, it says, what is the kinetic energy of the skateboard as it travels across the ground? So they're talking about, in this initial situation, what is the kinetic energy? Well, we know the velocity is 9 meters per second and the mass is 3 kilograms, so hopefully you can figure out 1/2 mv squared. This is just the same as the previous problems that we were doing in 8.4 kinetic energy when we were doing it in the textbook. We did those 5 problems. So you have 121.5 joules of potential energy. That's here. So this is 121.5 joules. Okay. For C, it says, as the skateboard travels up the ramp, all of its kinetic energy is transferred into gravitational potential energy. So it's being transferred. This kinetic energy now becomes gravitational because as it goes up, it's slowing down, so it's losing kinetic energy and gaining potential energy because it's increasing its height. And those two things happen simultaneously. As one happens, the other happens. As it loses kinetic energy, it gains potential energy. So it says, how much GP, how much gravitational potential energy does the skateboard have at its maximum height? Now, you might have tried to do GPE is equal to mgh because that's how we were doing it on 8.5 when we were doing these problems. And yes, we know what the mass is. Yes, we know what G is, but they don't tell you how high it goes. So if you tried to do that to find GPE, you ran into a problem. I don't know what the height is, but don't fear. That's the beauty of these problems. If you know the initial energy, that can help you find out what the final energy is. Luckily, we don't have any kinetic energy left over. It has all been transferred into potential. All right, all that kinetic is potential. So the kinetic energy that we just found it's still there, it's just in a different form. It's potential energy now. So this is 121.5 joules. No work necessary, which is why I didn't give you a lot of room. For 2, it says how much kinetic energy does the skateboard have at its maximum height? Technically, you could calculate it. You could do 1/2 mv squared, but they tell you that the velocity is 0 at its maximum height, which you should know. And when you do the problem, you get 0 joules of energy for the kinetic energy. The point of part C is just to it's like a scaffolding thing. It's telling you that you know what the potential energy is now, given the kinetic energy in the beginning. And that leads us to D. It says, what is the maximum height reached by the skateboard? So now you could do your GPE is equal to mgh, and this is 121.5 joules is equal to the mass, which is 3 times 9.8, and now you're looking for h, so you get h is equal to 4.13 meters. So that's your height. Now, before I do the rest of these, you should really be able to do the rest of them on your own if you just follow the scaffolded questions here. Before I do that, I'm going to do something that I don't normally do. I'm going to show the law of conservation of energy using that total energy formula we talked about in class. Basically, part C here is a way for you to determine conceptually how much gravitational potential energy there is. But without just like thinking about it and making the leap and saying, okay, let me use this value I got for the kinetic energy and put it in for GPE, why are we doing that? What is the math behind that? Can I prove it mathematically? And you can. So what we learned about in class was that the energy in the beginning, the total energy initially, is equal to the total energy in the final situation. Again, this is the initial situation, and this is the final situation where it's a height above the ramp. Now, we learned that the total energy in general is equal to the potential plus the kinetic plus this weird Q thing. Q stands for heat. So unless you have a surface with friction, you're not going to get a lot of heat. So that's what causes heat. Is anytime they say it's friction, you're going to have to deal with Q, internal energy or heat. So the total energy. So this is the total energy in general, but now let's do it for the initial and final. So I'm going to write those things twice. We have the potential energy in the beginning plus the kinetic energy in the beginning plus Q, but all right, we'll write it plus Q in the beginning, which is internal energy or heat, is equal to the sum of all the energy at the end, plus KE final plus Q final. Okay, now let's look at this. In the beginning, okay, how much potential energy do we have? Right here. It's on the ground, that skateboard. So there is no potential energy. But what type of energy do we have? It's moving. It has a velocity. It's very fast. You could see the fast lines going. It has kinetic energy, definitely. So we'll leave that. But it says it's a frictionless surface. Or if it doesn't say anything about friction, so we could ignore the internal energy. So initially, we just have kinetic energy. And now let's look at what we have at the end. At the end, the situation looks like this. All right, we're a certain height above the ramp. The skateboard's all the way up here now. So there is definitely potential energy. We like that. We want to keep that there. But is there any kinetic energy at the maximum height where the velocity is 0? No, it's not moving anymore. For a split second, it stops moving. So that's at the very top. It has no kinetic energy left. And again, there's no heat loss due to friction. It's a frictionless ramp. So, what do we have? This is the formula that tells us that we can make that jump. Yes. If we know what the kinetic energy is in the beginning, really, you could put I. If you know this kinetic energy here, then you know what the potential energy is here. and the final situation. So if we were going to take this formula one step further, we could plug in what we know for KEI, and that tells us what the potential energy at the end is. So I've done these problems a couple times, so I could kind of do that in my head, and I tried to make letter C scaffold that thinking for you, but if it helps, I don't know, some people like to write out this whole equation and analyze and see, okay, do I have potential energy in the beginning? No. Do I have kinetic? Yes. Do I have Q? No. And then at the end, I have just potential. So that means whatever I have in the beginning is equal to the potential energy at the end. And if you do more complex problems, sometimes there will be a potential energy and a kinetic energy at the same time, and then you'll have to analyze and calculate from there. But that's basically like behind the scenes what's happening as we do the conceptual stuff. All right, without any further ado, let's do number 2. 2 says a 4 kilogram block is pushed up against a spring attached to a wall and then released, free to travel on a horizontal frictionless surface. The spring has a spring constant of 30 newtons per meter and was compressed 0.6 meters. Draw 2 diagrams of the block and spring system. First, draw the spring when it was compressed, and then draw when the block reaches the equilibrium position. So again, we're kind of doing like the initial and final situation here. So here we have a very compressed spring attached to a block. It's a cart technically, and it's compressed a certain distance away from its equilibrium position. Maybe the spring was originally this long over here. Maybe this spring should be that long, and it was compressed. It's pushed back. We're exerting a force over this distance, so we're doing work on the spring, and that work is stored in the spring as elastic potential energy. So however much force times distance, however much work we do, that's equal to the elastic potential energy stored in the spring. And again, the mass of the block is 4 kilograms, and the spring constant of the spring is 30 newtons per meter. So this is like the initial situation here. The final situation that they talk about, it says to draw when the block reaches the equilibrium position. So you're pushing on this spring, and then you let go, and the spring pushes you back to the equilibrium position. So now it's making the cart move. It's giving the cart kinetic energy. So I'm going to try to make it this distance. That spring length should be about that long now. 1, 2, 3. Pretty good. Now this isn't a stretched out spring. It is a spring in equilibrium. All right, this is what the original length of the spring is. It's not stretched at all, so we can't even draw an X. You know how we drew the X over here? It's in equilibrium. There is no X. We can say X is equal to 0 meters. It's not being stretched or compressed. So there's no more energy stored in the spring. But the spring constant is still 30 newtons per meter. Now, it says, what is the elastic potential energy in the spring when it is compressed? 0.6 meters. So we know what X is 0.6 meters. So they're talking about this initial situation. All right, it says, what's the EPE? So again, hopefully you're able to do this. This was just like the problems we did on the homework 8.7. So this isn't really anything new. 1/2 times 30 times 0.6. Don't forget to square it. Your potential energy that you stored in the spring, the amount of work that you did in compressing the spring, the energy stored is 5.4 joules. If you compressed it further, you'd have more energy stored. If you didn't compress it as much, you'd have less energy stored. But as of now, with the amount of work you did in compressing the spring, we have 5.4 joules of energy to play with. No more, no less. Now it says when the block is released, the spring goes back to its equilibrium position. Here. All of the elastic potential energy is transferred into kinetic energy of the block. We said it's moving. This block is moving now. We don't know what the velocity is, but we know that there is a velocity. all of that stored energy has been transferred into kinetic energy. So, how much kinetic energy does it have? Well, if it had 5.4 joules of energy here, there better be 5.4 joules of energy here. Now, let's see. Is it a certain height above the ground? No, it's touching the ground, so there's no gravitational potential energy. In this position here, is there any added kinetic energy? Is it moving? No. All of the energy is elastic potential energy. Let's look over here. All right. Is it a certain height above the ground? No. Is the spring stretched or compressed anymore? No, it's in its equilibrium position. So all of that energy is now kinetic energy. So it's 5.4 joules. Again, you could calculate it by doing this formula here, but we don't really need to. We can conceptually do that little check mark game. All right, there's the three types of energy here: GPE, EPE, and kinetic energy. So in this situation here, does it have any gravitational potential energy? Nope. Is the spring stretched or compressed? Nope. It just has kinetic energy. How about in the beginning? It wasn't a certain height above the ground, so there was no gravitational potential energy, but there was potential energy in the form of elastic potential energy. The spring was compressed from equilibrium, okay, a certain distance, 0.6 meters. Was it moving? No, you compressed it and then you just held it there, so there's no kinetic energy. So all of this elastic potential energy is being transferred into kinetic energy. So for 2 it says, so that's how we figured out that it was 5.4 joules. All right, if this is 5.4 joules, this must be also 5.4 joules, because all of that energy is transferred just from one type to the other. And it says, how much elastic potential energy does it have at equilibrium? Well, it's at equilibrium, so the spring isn't stretched or compressed at all. If we did the calculation again, we'd have to plug in a 0 for x, and we get a potential energy of 0 joules. At D, it says, what is the velocity of the block when the spring is compressed 0 meters? So they're talking about this final situation here. What is the velocity of the block? Well, now that we know what the kinetic energy is, we could just do KE is equal to 1/2 mv squared. And the whole trick to this is now we could plug in the 5.4 joules that we calculated before for the initial situation. That's equal to 5.4 joules of kinetic energy in the final situation. So this is 4 kilograms times the velocity squared. You do the math and you should get about 1.6 meters per second. Very good. All right, number 3. Now it's saying a 2 kilogram rock is dropped from a 50 meter high cliff. What is the gravitational potential energy at the top of the cliff? So you could do GPE is equal to mgh. GPE is equal to 2 times 9.8 times 50. So this rock at the very top of the cliff has a gravitational potential energy of 980 joules. Then it says, what is the gravitational potential energy after it is dropped 15 meters? So did it go the full 50 meters? It certainly did not. So let's draw ourselves a little picture here. Let's see what we could do. Okay, here's the cliff. It's 50 meters tall. Here's the rock. Initially it has 980 joules of GPE. Okay? But then it falls 15 meters. It's still a certain height above the ground. How high is it above the ground now? You have to do 50 minus 15, and you get 35 meters. That's how tall, that's how high the rock is above the ground. And it says, what is the gravitational potential energy after it is dropped 15 meters? So now we're looking at this situation here where it's 35 meters in the air. So you could say GPE is equal to mgh. GPE is equal to the mass times 9.8. But the height is this new height it's 35 meters in the air. So we could call this like H2 and GPE2 if we really wanted to for like the second situation. So you get 686 joules. So it decreased. We had 980 joules of potential energy initially, but then after the rock fell 15 meters, now we have a gravitational potential energy of only 686 joules. So it went from 980 to 686. How could your energy decrease like that? It must have gone somewhere, right? Law of conservation of energy says that you can't create or destroy energy. So part C says, what is the kinetic energy after it has dropped 15 meters? And it even gives you a hint. The total mechanical energy does not change. The GPE at the top is equal to the total energy during the fall. After dropping 15 meters, some energy is kinetic and some is potential. So if we look back at our diagram, by just drawing the potential energy, we're not giving the full story. There is some kinetic energy here because obviously the ball is falling down. It has some velocity at this position shown right here. All right, so what is the kinetic energy? Well, if you're comfortable with the concept of conservation of energy, you could just say to yourself, well, I had 980 joules in the beginning. Now I only have 686 joules of potential energy at the end. Whatever the difference is must be what my kinetic energy is. So it should be 294 joules. That's my kinetic energy. Boom, shakalaka, done, moving on to the next one. But if you're not sure why I'm doing that, that's fine. We just got to use that calculation that we had. We had the initial total energy in the beginning should be equal to the total energy at the end. So this would be our initial, and this would be our final situation. So initially, it's up here. It's dropped from rest. So we have PEI plus KEI plus Q, internal energy, is equal to PEF plus KEF plus Q. Now, in the beginning, it's all potential energy because it's dropped from rest, so there is no kinetic energy. Let me zoom in. All right, the kinetic energy in the beginning is 0, and we can assume this is frictionless. We'll ignore air drag, and it's 0 here. So initially, it's all potential energy, that 980 joules in the beginning. Then at the end, let's look back at our diagram. There is some GPE here. We're still a certain height above the ground. We're 35 meters above the ground, so you can't cross that guy off. We have potential energy, plus we're moving. All right, we're picking up speed. Even though we have less potential energy, we're picking up speed. We have more kinetic energy than we did before. Before we had 0 joules of kinetic energy. But now, this is KEF, and this is 0 because we're ignoring air resistance. And look at this equation now. We have PEI is equal to PEF plus KEF. All right, so the initial potential energy we said was 980 joules. Then we calculated it up here in the second situation where it's 35 meters above the ground. You only have 686 joules of potential energy plus whatever kinetic energy you have. That's the total energy in the final situation. And now, as you can see, you have to subtract 686 from both sides. Hey, that's what we just did in our heads over here, because we knew that the difference in the potential energies is going to be whatever our kinetic energy. So now we have that is 294 joules. Okay, another long-winded answer on where we got that from. I mean, if you've done a bunch of these and you're comfortable with it, technically you could get away with just doing the subtraction, finding the difference. This is the long, drawn-out way, which is good to know. Conceptually, believe it or not, if you could do this, you're doing this in your head, okay? And we're just writing it out mathematically and proving it mathematically. So D says, what is the speed of the rock after it dropped 15 meters? So what is the speed at the position shown here? So you could do KE is equal to 1/2 mv squared, and you just use the kinetic energy that we found. It was the potential energy lost by the rock. 294 joules is equal to 1/2 times the mass times the velocity squared, and you get a velocity of about 17.1 meters per second. Okay, number 4. A child does 0.35 joules of work to compress the spring in a 0.02 kilogram pop-up toy, kind of like a mini pogo stick. I was trying to describe it like this. Okay, so you're compressing the spring a certain distance x. All right. After releasing the spring extends to its equilibrium position, shooting itself into the air. What is the elastic potential energy of the toy when it's compressed? This is an interesting way to frame this. If you look at the givens, it says a child is doing 0.35 joules of work in compressing the spring. All of that work is being transferred into elastic potential energy in the spring. So they're telling you this is 0.35 joules, no math necessary. Now it says, what is the kinetic energy of the toy when it reaches its equilibrium position? When it's in its equilibrium position, there is no x. So if we try to do PES is equal to 1/2 kx squared, x is equal to 0. So there is no potential energy anymore. All of this potential energy stored in the spring has now been transferred into kinetic energy. So this is going to be 0.35 joules as well. So now it's shooting itself up into the air, and it says, what is the gravitational potential energy of the toy when it reaches its maximum height? So you have the compressed spring, and you got this spring compressed by exerting a force over a certain distance. And the force times distance, that was equal to the work done. So the work done is equal to the potential energy stored in the spring. Now the spring pushes itself back up to its equilibrium position. When you let go, this is the spring in equilibrium right here. There's no more elastic potential energy anymore. All of that elastic potential energy, it's moving. It's being transferred into kinetic energy. And it's not attached to the ground at all. Even though this looks like a suction cup, it's not a suction cup. It's just like a little plastic base for it. And we know that this thing has some inertia. So now it's moving upward. The mass of the toy is going to make it continue to move upward until gravity pulls it back down. So now it's going up, slowing down to a stop here, a certain height above the ground. Okay, good. Again, this distance, so over here I just noticed I didn't change this to an x. That should be, we could call that x. And now we have the situation. In the beginning, it's all elastic potential energy. Then it gets transferred into kinetic, which causes it to have gravitational potential energy at the top. And it says, what is the maximum vertical height that the toy can reach after the spring is released? Well, we know that this has a potential energy of 0.35 joules. Because whatever work you did on the system in compressing the spring, that total amount of energy is going to stay the same throughout the whole experience. So now we have GPE is equal to MGH. This is 0.35 is equal to the mass, which they tell you is 0.02 kilograms, times 9.8, and we're looking for the height. You do the math, and you get a height of 1.63 meters. So that's a pretty, it's actually pretty tall. 1.6 meters, over 1.5 meters. Think of 1.5 meter sticks. All right, pretty good. Let's do number 5. Number 5 says a 0.5 kilogram toy car is moving 4 meters per second on a horizontal frictionless surface. What is the total work that must be done on the toy car to increase its speed to 12.5 meters per second? So you have the car, and it's initially traveling already with some velocity, 4 meters per second. It has some kinetic energy. We're not sure what it is yet. and then you push on it. Oops, there's no hill there, just a straight line. And now you exert a force over a distance, causing this to get faster. All right, so you have more velocity now. It's 12.5 meters per second. There's even more kinetic energy here. Now, the work kinetic energy theorem, we're shifting gears now. We're going back to this. The work kinetic energy theorem states that the total work that you do is equal to the change in the kinetic energy. So this kinetic energy increases. It's definitely getting faster. Started at 4, now it has more kinetic energy. It's moving at 12.5 meters per second. Where did it get this kinetic energy? It's equal to the work that you did in pushing the block of a certain force times the displacement. All right, so the work is equal to KEF minus KEI. So W is equal to 1/2 mvf squared minus 1/2 mvi squared. You could solve for this however you want, really. You could do this on the side, and then you could do this on the side, and then you could subtract them both. That's totally fine. You could start plugging in numbers as it is here. But for me, it's actually easier if I pull this out, 1/2 times m. So it's in both terms. So you could pull out 1/2 m, and then you're left with vf squared minus vi squared in parentheses. And you can continue your work over here. Now let's plug in some numbers. 1/2 times 0.5 times vf squared, 12.5 squared minus 4 squared. And I'm going to move that down. Okay, and you get a work, how many joules? You get 35.0625. So let's just round that to around 35 joules. Okay, no matter how you did the math over here, you should still get the same difference in the kinetic energy, and that's equal to the energy that we added to the system. All right, so that's equal to the work that must be done. Work kinetic energy theorem, throwback for sure. All right, now it says a 0.5 kilogram ball is dropped from 4 meters high and bounces back to a maximum height of only 3 meters. How much energy is transferred into internal energy? What the heck? Oh man. All right, so let's see. We have a ball above the ground. Oh, another weird looking ground. Hold on. There's the ground. It starts, and the height is 4 meters. Oops. And then the ball bounces, and you've probably experienced this in the real world. It doesn't come back up to the same exact height. It keeps losing height. It's not going to just bounce forever. Now it's at a different height. It's at 3 meters. We could call this HF, HI, or H1 and H2. It's really not the final height, but for this situation, it is, because they're just saying at 4 meters and at 3 meters. All right, and the mass is 0.5 kilograms, and G is equal to 9.8 meters per second squared. Don't want to get point off for my units. All right, so it says how much energy is transferred into internal energy. We have to do, first let's find the potential energy at both these heights. So we have GPE for the initial, and it definitely still has some GPE in the final, and technically it's at the maximum height here for both situations. There's no kinetic energy at these maximum heights. It's all just potential energy. But you're going to have less potential energy. If you do GPEI is equal to mghi, you have GPE is equal to the mass times 9.8 times 4, and you get 19.6 joules of potential energy initially. But then you do the same thing again, but you plug in your new height of 3 meters, and now you only have a potential energy of 14.7 joules. It was 19.6 before. What the heck happened to that energy? Now it's 14.7 joules. It bounces down and then it comes back up to a maximum height before bouncing down again. So here the velocity is 0 meters per second. so there's no kinetic energy. There's no spring involved, so there's definitely not any elastic potential energy. Where did the energy go? It actually went into internal energy, which is like sound, vibrations in the air. It's heat from the vibrations in the floor. You're vibrating the particles, so technically that's causing some heat there. So how do you find that? Again, you could just find the difference between the two, but if we wanted to write a nice equation, we definitely could do that. Let's write it down below right here. All right, so we have the total energy initially is equal to the total energy at the end. And again, the total energy is just the sum of the potential plus the kinetic plus Q internal energy. And then you have potential plus kinetic plus Q. And this is for the initial situation. This is for the final situation. All right. Initially, we're talking about when the ball is 4 meters in the air. You let it go. It didn't go through the air yet. There's no air resistance due to friction. It didn't hit the ground yet. So there is no internal energy yet. You release it from rest. So it's just the potential energy in the beginning is equal to. Now the final situation is when it's 3 meters above the air. All right, so now you're not as high as it was before, but you definitely still have some potential energy. And hold on a second, we said you're not moving at the top, so there's no kinetic energy either. So this is no kinetic energy, but it says it's transferred into internal energy. That's where the energy went, into that weird Q thing. All right, so that's Q. So the initial potential energy is equal to the final potential energy plus whatever energy we have in the form of internal energy. You do the subtraction and you get an internal energy of 4.9 joules. All right, so that's where the energy went. All right, that's about it. You could comment below. I realized that I could zoom in and out on this page. Let me know if you like that type of thing. That way we could draw some nicer diagrams like up here. All right, this is a super tiny diagram, but when I zoom in like this, that's pretty good. But I wasn't really sure. It looks like it's blurry on my screen when I do that. Is it better if I pause and zoom out like this, and then I can pause and zoom in? That way you don't have that weird lagging thing, and I'm not making you guys motion sickness, whatever it is. Anyway, I could do it like, see, like, you guys like that? I don't know. Comment below. Let me know. Let me know if I shouldn't zoom in at all. I'm thinking about I'm going to zoom in, though, because it makes the experience less static. It makes it really dynamic. Whoa, we're learning physics. Crazy. All right, have a good day.